Hello physics students. So in the last video, you learned that current created a magnetic field. In the case of electric field, it was charge. kq over r squared, the magnitude of the electric field caused by a proton or electron. In the case of magnetic field, it's current, the magnitude given by mu 0 I over 2 pi r. And then we also learned that the direction was more complicated than the electric field. In the case of the electric field pointed either away from a proton or towards an electron. But in the case of magnetic field, the magnetic field wrapped around a wire. So we had a pattern like this, okay? If the electric current were coming straight at you, it would wrap around the wire like that. So we needed a little tool to help us figure out the direction. The right-hand rule, you put your thumb in the direction of the current and your four fingers wrap around like this. Today we're going to learn about the magnetic force, which is also more complicated than the electric force, which was just QE in the direction of the electric field or against it. So there's a new formula, and the direction, not so simple. We get another right-hand rule to find the direction of the magnetic force. So there are two different right-hand rules. So what I want to do today is begin with a set of demonstrations to show you, to give you practice using the first right-hand rule before we move on to the second one today. So I did these another day in our classroom, so I've got to use our time machine again to send you back so you could watch those demonstrations. But I want to say this, when I show you demonstrations today, don't watch passively. If we were in school, what I would be doing is I would be watching everyone and I would not move on until I saw everyone doing the right-hand rule and answering. Well, I can't do that today, so it's up to you. You've got to watch carefully and do the right-hand rule and come up with an answer in the pause during the video and then watch so you get practice. Because if you wait till the test to figure out these right-hand rules, you're going to get the questions wrong. All right, enough. I'm going to send you back, so brace yourself. So I'm now going to demonstrate how we could use this right-hand rule that we just learned to figure out the direction of the magnetic field around a current-carrying wire. Before I do that, though, I want to first talk about permanent magnets. What I have here is what we call a bar magnet. It's a piece of iron that's been magnetized, has magnetic properties. You might be looking at this and saying, wait a minute, I don't see any current here. How could there be magnetic field caused by this magnet? But there is current. There are little currents because, as we know from chemistry, there are atoms, and atoms have electrons orbiting around a nucleus, and so the electrons orbiting are the tiny submicroscopic currents in this bar magnet that create the magnetic field. Normally, substances do not create magnetic field, like, for example, a piece of styrofoam, because the orbits of all the atoms are randomly aligned, and so the magnetic effects tend to cancel for the whole object. Iron is special, though. You can align these atoms so that they have a permanent magnetic effect. Now, the magnetic field comes out of the north end of a bar magnet and goes into the south end. And so that's how the magnet comes out this way, in this way. And the other thing that we know is that magnets interact with each other. For example, if I bring, this is the North Pole here, and I bring the North Pole of this magnet here and I let go, you'll see a repulsion. Whereas if I bring the South Pole near, the North Pole near the South Pole over here, you'll see an attraction. So like poles repel, opposite poles attract. Now, you might notice too that this magnet tends to always turn so the north end points towards this direction. And the reason why is, as you know, the Earth has magnetic properties also. It's itself a giant magnet. But here's an interesting thing. If the North Pole of this magnet is attracted to that direction, which is north on the global scale, that means that this being north, what's at the North Pole of the Earth, geographic North Pole, is actually a magnetic South Pole. The reason for this sort of discrepancy is a historic mistake people made when they first studied magnets. They said, hey, look at this end. It points toward the North Pole. This is what we're going to call the North Pole because it points toward the north. And really, they didn't realize, well, the reason why it pointed toward the North Pole is because there was a magnetic pole at the North Pole. If you want to call that north, then this should have been called south. So everything got kind of switched around. But regardless, the point is that magnets that are free to swivel will align to the Earth's magnetic field. That's what we have here, a smaller scale, a little tiny compass, which hopefully you can see on the screen. And what, actually, you know what I'll do is I'm going to reconfigure, but before I do that, so you can see a closer view of this, I just want to call your attention to the fact that this wire is connected to the positive terminal of the power supply. The current will come through this and go this way, and it's going to be going this way. Okay, so on your screen, that's from right to left, the current is going to be going and into the negative. So let me pause and reconfigure the camera so you get a close-up view of this. So here's that wire again, and the little compass, which is just a bar magnet that's able to spin. And as I mentioned, the Earth's magnetic field points in the direction as indicated on this piece of paper. And so the compass is lining up with the Earth's magnetic field. In other words, the red needle of the compass points in the direction of the magnetic field in the vicinity of the compass. Now what I'm going to do, so right now only Earth's magnetic field is responding to. I'm going to turn the power supply on. It'll make the current pass this way through this wire. And the compass is above the wire. What I want you to do is use that right-hand rule that you just learned to determine the deflection of this compass needle. Which way will it point when I turn the current on? So I'll create a pause, figure it out. All right, so now let's see again, current's going to go this way. I'll flip the current on, and you see that the needle deflected this way. So let me put a label like this, and I'm going to zoom out because my hand's too big for this setup. And you see, there's the direction of the wire's magnetic field above the wire. Let me go out a little bit more. So how could we have figured that out? Let me see. Oh, I guess I got to go further out. Well, as you can see, the current, as I said, the current goes this way. So I put my right thumb in the direction of the current in the wire. So the magnetic field wraps around that wire, and above the wire, it comes toward me that way, as you can see indicated by the arrow. So the next thing, what would happen if I flipped the current around? What I'm going to do is I'm going to switch the terminals here so now the electricity will be going in this direction instead of that direction. What I want you to do is use the right-hand rule to again figure out the new way this compass will flip. Well, obviously it's the opposite way, right? We know that, just common sense. But practice the right-hand rule. Above this wire, with current going that way, which way will the magnetic field go? All right, well, here we go. Let's turn on the power supply, and we see the needle go the opposite way now. So it goes like this, okay? That's the B of the wire. And let me zoom out and show you how you can figure that out. So again, the current went this way, so I put my thumb in the direction of the current. My four fingers tell me the way the magnetic field wraps around. So then underneath the wire, the magnetic field will be going this way, but above the wire, if I twist my hand around, you see that the magnetic field does go that way as indicated by this and the compass needle pointing direction of the magnetic field. All right, so that's a demonstration of the magnetic field caused by a current carrying wire. All right, so that was practicing finding magnetic field using right-hand rule number 1. let's move on to finding the magnetic force. So the symbol is F for force and then B for coming from the magnetic field. Here are a couple examples. A proton and electron and the magnetic force they experience. Notice there's a velocity in both cases, and that's not an accident. You could have the most powerful magnet in the universe and put a proton or an electron there right next to it, there will be no magnetic force. You've got to have a velocity in order for there to be a magnetic force. The other thing is the velocity cannot be parallel or the opposite direction of the magnetic field. It's got to be off in a second dimension, at least a component of it. And then finally, these are the forces in a third dimension. Dimension 1, dimension 2, third dimension, same thing. So magnetic force is always a three-dimensional consideration. But how do we find that direction of these forces? So that's where the second right-hand rule comes into play. So I'm going to create a pause to allow you to copy these down, and then we'll apply and see if we can generate those forces using these rules. So go ahead and copy these down. Okay, so let's go on and try this example first. So first we point our right index finger. Remember I said in the last video, sometimes students, I don't know why I'm getting it wrong, and they're using their left hand. Make sure it really is your right hand rule. It's a right hand rule. You point your index finger, that's this one, the pointer, in the direction of the velocity like this, right? So that's lined up there. I won't go like this because you won't see what's going on. So I'll just do it down here. Swivel your wrist with the index finger unchanged so that the three fingers point in the direction of the magnetic field. So don't do this, because see what happened? My index changed. Imagine that you're like sticking your finger into a pipe. And so all you could do now is go like this. Okay, so I'm going to swivel and get these fingers to point in the direction of the magnetic field. They're pointing toward the top of the screen. And then the last thing you see that the thumb points in the direction of the force on a positive charge. And this is positive, so the force is out of the screen or out of the board. Okay, so this is the awkward shape that you have to make for this right-hand rule. Okay, like this, compared to that, it's this for force. All right, so I'm going to create a pause. In case you didn't do that, you were just watching. You do that on your paper. Do that right-hand rule and see if you come up with the same answer. Okay, so let's now apply the same rule to this electron moving. So what I'm going to do is again put my index finger in the direction of the velocity like this. Now I have to swivel my wrist so that my three fingers point in the direction of the magnetic field. So I need to get them to point out of the board. So let me do this because that's B. So there. Oh, okay. I can't quite get there. So let me try going this way. All right. There. I've achieved the three fingers here pointing in the same direction as the magnetic field while maintaining my index finger like this. I see my thumb points to the bottom of the screen, and that would be the force if this were a proton. Since it's an electron, it feels the force in the opposite direction. So there is that applied to, the right-hand rule applied to this. What I'm going to do is create a pause, practice it again. Don't move on until you can achieve this. As you saw, it got a little awkward for me, so I went the other way. You have an even greater advantage. You have your piece of paper, which you could just start turning around and making it convenient, swiveling the paper around. So go ahead and do that practice. Okay, that's the direction. Now, the magnitude. So, but I also want to point out one other thing. The force is, as I said, always perpendicular to the velocity of the magnetic field, but these don't have to be 90 degrees apart. They could be anything but 0 and 180, because this is the force QVB sine theta. Okay, so you need a charge, you need a velocity, you need a magnetic field, and you need an angle that's not 0 or 180 to get magnetic force. Another point, that the magnetic force is a maximum if you plug in 90 degrees. The velocity and the magnetic field are 90 degrees to each other, and it's 0, as I said, for those angles. Now, what I'm going to do is send you back again to another demonstration where I have something called a cathode ray tube, so you can practice the other right-hand rule with that, a beam of electrons. More practice. We had the wire one. Now you're going to have this practice with the cathode ray tube and a beam of electrons. So brace yourself. You're about to get sent back in time to another demonstration. So what I have here is a glass tube that will provide evidence that I can create an electron beam inside this glass tube if I supply a high enough voltage to it. To prove that, what I have is a circular metal plate inside the glass tube here, which you could see inside, connected to this metal post up here. And on the other side, we have a similar circular metal plate connected to this post over here. Also inside this glass tube is a metallic paddle wheel that's balanced on this glass track, and it's slightly declined this way, so there's a gravity component of the gravitational force that keeps the paddle wheel on this side of the track. Now I'm going to create an electron beam flying this way from left to right. So in order to do that, I need to take this high voltage power supply and hook the negative side of it over here. That'll repel electrons away that way. And a positive, this will be charged positive to track them this way. Now this is actually a little bit clearer, I believe, if I move this out of the way, a little easier to see. So I'm going to flip this on and we'll see evidence of that electron beam going this way. As you can see, the paddle wheel is displacing to the right because of the collisions with the electrons. Even when it bounces off the right side of the track, the electrons keep hitting that paddle wheel and moving them back to the right. When I shut off the beam, then the gravity component pulls it back down to this side of the track. What I'm going to do is use this same power supply in a different tube to show you evidence of the magnetic force on a beam of electrons, and also show you evidence that, yes, the right-hand rule works for that electron beam. So let me reconfigure the can. To create magnetic force, I obviously need a magnetic field. So the source of the magnetic field in this demonstration will be a bar magnet, a permanent magnet. The other thing that's true of a bar magnet is that the magnetic field comes out of the North Pole and into the South Pole. So this has magnetic field coming out this way, B going that way, and B going in this side, the South Pole. So what I'm going to do is I'm going to now take this tube here called a cathode ray tube, and it's hooked to the same high voltage power supply. Negative side over here, and that means the electrons are going to be shooting from left to right like this with a velocity. And what I'm going to do is I am going to put the south pole of the magnet, this end, the blue end, behind the beam. And what I want you to do is use your right-hand rule to figure out which way the beam will deflect. The velocity is going to be going this way. The magnetic field is going to be going away from you into the screen. Okay, so I'll create a pause and let you think about that deflection. All right, so what you should have done is you should have said, okay, velocity this way, my four fingers already into the screen like this. For the magnetic field going into the South Pole over here, and my thumb points up. What that means is that if these were protons, they would deflect upward toward the top of the screen. But since they are electrons, they deflect in the opposite direction of my thumb, in other words, down. So we should see this beam, before I put the magnet there, going straight across and then curve down when I bring the South Pole near. Let's see if that's what we see. So there's the beam, straight across. You see a green line. It's hitting the gas molecules inside this tube and creating a green effect like that. Here comes the South Pole of the magnet, and you see the beam does, in fact, deflect downward. Okay, so that's evidence of the right-hand rule working, again, that the electron goes down. Now, what happens if instead I put the north pole over here? So use the right-hand rule in front of the glass tube here. Here's the north pole like this. Figure out the deflection of the beam now. I'll create a pause to allow you to do that. Okay, let's see what happens. The beam is straight across, and now here comes the magnet, and you see once again it deflects downward because now instead of a south pole creating magnetic field going away from you, over here, the south pole pulling in the magnetic field like this, I put a north pole over here, which is a source of magnetic field going this way again, so away from you. So that's the same magnetic field. Whether I put a north here or south here, the magnetic field goes like that. Obviously now, if I go the other way and I put a north pole going behind here like this, it's going to deflect the opposite way. But what I want you to do is practice the right-hand rule and see if you can figure out that the deflection will be up this time. So I'll create a pause. All right, so let's see it happen first. You see I put the north pole close and that beam is deflecting upward towards the top of the glass tube. Why? Well, this is going to be a little bit tricky, but I have my velocity still this way, right? From the negative side to the positive. Then the magnetic field, there was a north pole back here, magnetic field coming this way out of the screen. So what I have to do is now turn my wrist without changing my index finger here, because that's the velocity. So I turn my wrist and it's like this. It's like physics class yoga, right? Holding my wrist like this, right? And so it's a little awkward, but that's how the right-hand rule works. My thumb is pointing toward the bottom of the screen. That would be the force on this beam if it was made of protons. But since it's made of electrons, it feels a force in the opposite way of my thumb up toward the top of the screen. It deflected up. So this tube deflects and shows not only that magnetic field causes force on moving particles, but also that this right-hand rule gives us the direction of the magnetic force. Okay, so welcome back. Hopefully you were able to apply the right-hand rule number 2, this right-hand rule, correctly to the electron beam to figure out the force and the deflection of the beam. Now, before I move on to examples of calculating the magnetic force, I want to take a step back and just talk about the theory of multiplying vectors. Because this topic, multiplying vectors, this idea is bigger than physics. Yes, if you major in physics, you'll have to know how to multiply vectors, but also in engineering. Or maybe you don't take any science at all and you just major in math. You have to know how to multiply vectors. Now, when you were a little kid, very young, you learned how to multiply numbers. Like, for example, the numbers 2 times 3. You learned that was always 6. When it comes to vectors, 2 times 3, a vector of 2 times a vector of 3 might be 6, but 2 times 3 could also be 5, or 1, or 0, or even a negative number. So it's more complicated to multiply vectors. Furthermore, there are actually 2 different ways to multiply vectors. And so that's what I want to do. I want to just take a step back and show you the 2 ways to multiply vectors using 2 vectors with some well-known formulas that we've used in physics. So the first is the vector dot product. Then we're going to learn the vector cross product. So you notice this formula here. Magnetic force is achieved or found by the vector cross product. But when it came to finding work in mechanics, or even earlier this year, we learned that it was the dot product between force and displacement, or if you wanted to convert it to a simple algebraic expression, FD cos theta. But what is this dot product? Well, let's take 2 vectors that are 2-dimensional. A force that has an x and a y component, and remember this I hat is a vector that has a length 1 that perfectly points in the x direction. The j hat is a vector that has a length 1 that perfectly points in the y direction. So we have these components of force in the x and y direction, and then we've got a displacement in the x and y direction. To figure out the answer of what this product is, the dot product. We're going to distribute these two binomials through to each other. So for example, we're going to take this first term and multiply it by here, the first term over there and the first term over there. So that's going to give me fx times dx. And then the I hat dot I hat is also part of that term. And then the x component multiplied over to the y component. So I could say fx times dy, and then the I hat dot j hat. Okay, the next thing I'm going to do is I'm going to take this second term and multiply it over to these two terms. So I will, on the new line over here, because I'm out of room, say plus fy times dx, but I still have the j hat dot I hat here. And then the fy term times the dy term, but I have the j hat dot j hat also in this term. Now, what do these dot products mean? This I hat dot I hat, I could determine using this other definition of a dot product. As I said, these have length 1 times the cosine of the angle between a vector in the x direction and the vector in the x direction, 0 degrees. So if you do 1 times 1 cos of 0, this term ends up being 1. And then this is 1 times 1, and x and y directions are 90 degrees from each other. So we do 1 times 1 cosine 90. And this term right here is 0. Same here. Y direction and x direction, 90 degrees apart. This term is 0 also. And then this is 1 times 1 cos of 0 degrees. This term is 1. So all that survives this product is this term, fx dx times 1. So I'll just do fx dx. And then this is 0, and we get fy dy times 1. And that is the work. That's how we perform a dot product with these components. Okay? Another thing I want to point out is that this is a scalar. In other words, it has no direction, it's just a number. It could be negative though. So again, 2 times 3 is 6 times the range of cosine values, which is from positive 1 through 0 to negative 1. So any number between 6 and negative 6 could be the answer of dot producting two vectors 2 times 3. Okay, 2.3 I should say. So there's the answer for the dot product. Now let's take a look how we would perform a similar operation with two vectors, but with a cross product instead. We're still multiplying vectors, but with a different kind of multiplication process. So we proceed in a similar fashion. What I'm going to do is say q times, the q is out in the front. I'm basically multiplying these two vectors, the velocity with an x component, the velocity with a y component, the magnetic field with an x component, magnetic field with a y component. So the first thing I'll do is, maybe I'll use green, take this first term and distribute it over to these two terms over here. So in other words, Vx bx, and then the I hat cross I hat is also part of this term. And then the Vx times the By, multiply it over. And then the I hat cross J hat is also part of this term. So that's the first term distributed over. And then, maybe I'll make a little bit more space. So then I will next take this term and distribute it over to those two terms. In other words, Vy bx and then j hat cross I hat. And then the Vy times the By and then the j hat cross j hat is also part of this term. And I've got to close out my brackets because it's q times all of those terms. Now, what I have to do is, before I evaluate this, I've got to figure out what these cross products are using this formula for the cross product, this definition here. By the way, this was plus the right-hand rule. This time, plus the right-hand rule. I'll talk about that in a second. So I've got to do I cross I. In other words, 1 times 1 sine of 0 degrees, because that's the angle between x and x. No angle. So in other words, this term is 0, according to this definition. I hat cross j hat. Well, first of all, the magnitude of that is 1 times 1 sine of 90 degrees, right? The x and y directions are 90 degrees from each other. So that gives me a magnitude of 1. But a cross product has direction with the right-hand rule. So how do I figure that direction out? Well, maybe I'll do it here. X, y, and then z would come out of the board like this. So if I do the cross product, the right-hand rule with x direction cross y direction, so I swivel my wrist until my 3 fingers point in the y direction. I see my thumb points in the positive z direction. So I cross j gives me plus k hat. Not a scalar, but a vector of 1 in the z direction. J hat cross I hat. Again, I have 1 times 1 sine of 90 degrees. The magnitude of this is 1, but what's the direction with the right-hand rule? So I have to take my y direction first, right? So j hat cross I hat. So now I have to swivel my wrist. So my 3 fingers here point in the x direction without changing this one. I'm swiveling around and I see my thumb points into the board. In other words, the opposite direction of z, or negative k hat, is the multiplication of, cross multiplication of these two. And then lastly, j hat cross j hat, 1 times 1 sine of 0 degrees between y direction and y direction, which is also 0. So the only terms that survive are these two. And so I do, FB will be the Q term in the front, VXBY, and since this is a negative K hat, I'm going to do this, minus VYBX K hat. And there's the answer of a cross product with two vectors. So let me create a pause first to allow you to copy all this down. All right, so the cross product gives you another vector. So 2 times 2 cross 3 can give me a vector any length between 6 and 0, and the direction can be either up from those 2 arrows or down from those arrows. So again, like plus 6 and negative 6 or anything in between, but there's a direction associated with cross product generates another vector. Dot product generates a scalar, a number without a direction. So let's add that here, vector. So like I said, this is more than physics. This can go into math. Actually, Calc 3 in college, you have to know how to do cross products and dot products with derivatives. So it has a lot of applications, and you need to know how to do this because it's part of the physics curriculum, but also know it for later in life when you're studying in more detail. All right, now I want to do some examples of the magnetic force, some calculation examples. So let's move on. Okay, so here's the velocity, here's the magnetic field. We want to determine the magnitude and direction of the force on the electron. So rather than do this cross product, it's more convenient to use this formula here and the right-hand rule. So we could do the right-hand rule first to figure out the direction. So I put my index finger in the direction of the velocity, right, like this. And then what I need to do is swivel my wrist so these three fingers now point in the direction of the magnetic field, which is up like this. So I have to turn like this, and you see I have this aligned with B and this aligned with velocity. My thumb comes out of the board. That would be the force on a proton. This is an electron, so it feels the force the opposite way into the board. So let's do that and just mark that as the answer for the force into the board. So we have the direction. Now we need to find the magnitude. So we apply FB equals QVB sine theta. So the electron charge, I'm not going to put the minus sign in because we already determined the direction of the force. We're just going to look at the magnitude. And the charge of an electron is one elementary charge. We had this earlier in the year, 1.6 times 10 minus 19th coulombs. And then the velocity is 2.5 times 10 to the 5th meters per second. The magnetic field is 0.2 Tesla. And the angle, well, if you look at this, and if I were to go like this, 30 degrees here, then this is 60 from here to here, that's 30. So actually the angle between the magnetic field and the velocity is 90 degrees. So that just comes out to 1. And if we multiply that out, we get 8 times 10 minus 15th newtons. Okay, so there is the magnetic force. Let me create a pause to allow you to copy this down. Okay, so pretty straightforward example, but obviously you could be asked to solve for anything in this formula through algebra. Maybe we know the force, the charge, the velocity, the angle, and we're looking for magnetic field. Obviously, you know, any kind of example like that. So the next example that I'm going to do is one that involves actually taking the cross product, which I'm erasing here, but in a specific case. So let's take a look at that. Oh, by the way, one other thing, this, like all forces, you can possibly calculate the acceleration if they ask you. So this would be 8.0 times 10 to the minus 15th newtons. It creates acceleration like all forces. The mass is 9.11 times 10 to the minus 31. Remember, that's the mass of an electron, which you could look up in your textbook. And then you can get the acceleration if need be. I think it came out to be is 8.7 times 10 to the 15th. And in the future, we're going to look at, in the coming video, what kind of motion that acceleration creates. All right, so that's another topic. So let me write out example 2. Okay, so here we have the velocity in component form, magnetic field in component form, and the charge. So what we're going to apply is the vector cross product here. So we do that by first writing out FB equals QV vector cross B vector. In other words, 2 times 10 to the minus 6 coulombs is the charge. And then V is 4. Okay, so there's velocity and magnetic field filled in. So what I need to do is distribute this to that, and then distribute this to that. Okay, so let's go ahead and do that. So we've got, so then we have this times that, but we also have I hat cross k hat as part of this term as well. And then we're going to subtract this, well, maybe I'll do plus, negative 0.5 Tesla. All right, so we're going to multiply this, times distribute that 2 times, so that's going to be negative 4 times 10 to the 5th, no, 10, let's see, negative 0.4. That's this times this times this, okay? And then we have to do this I hat cross k hat. So again, we have our, well, yeah, I guess I can do x, y, and then z. So I hat cross k hat. Well, maybe I should do. So I have to do this I hat cross k hat. So I got to get these 3 fingers to come out of the board. I can't do it this way. Let me turn this way. And so I have I hat cross k hat. My thumb points down, which is negative j hat. So that's the result of the vector cross product on those 2 vectors. Then I have 2 distributed to negative 0.5 times negative 2, which gives me, if I multiply that out, is negative 0.2 newtons when I multiply those 3 numbers together. And then what I have to do is do this cross product j hat cross k hat. So start with j hat, and then cross with k hat. I got to swivel my palm to align these 3 fingers with k hat, and I see j hat cross k hat equals positive I hat. So, and that gives me my answer. So I have negative 0.2 in the x direction and positive 0.4 in the y direction. And there is the magnetic force found through vector cross product. So let me create a pause to allow you to copy this down. All right, so recap. We learned how to calculate the magnetic force, more complicated than the electric force, which was just QE, and either in the direction of E or opposite the electric direction of electric field. We have to use QVB sine theta, so you need a charge and a magnetic field, but you also need a velocity. And they can't be in parallel to each other. You have to have QVB sine theta. And then the direction is not so simple as in the direction of the magnetic field or opposite. Neither. You have to use this right-hand rule, velocity, magnetic field, force on a positive. Okay, so this rule here. So that's the magnetic force. I hope you enjoyed the video. I'll see you in the next physics video.